Well, the setup is basic enough, but how fast is that marble moving across the table? 1, 2 photo gates connected to a timer, which starts the clock at one gate and then stops it at the other, just like a stopwatch, but more reliable, more significant figures, giving us a good time. But we want speed, so we'll need distance also. Recorded, multiple trials showing us the consistency, and maybe some premature rounding, more on that later. A second distance now. Ready, set, time. Recorded, and you get the idea. More distances and more times, more consistency, but again, what's the speed? That's a good question, and a familiar equation, yielding 5 different values for speed. So we will average these together to get a final answer. Right? Well, not quite. This, by definition, is the average speed for the 70-centimeter trip. It's total distance divided by total time. This is the average of the averages, which maybe sounds better, but is it worth another significant figure or two? We know one thing: uncertainty exists, more or less. And I'm having a little bit of rounding regret right now. Still, it's good data. I mean, just look at it. Linear to be sure, although not perfectly so. Let's play connect the dots and find the slope of each segment, which is different than what we did before, you see? Well, anyway, one stands out. It's concerning, but not part of an overall pattern of speeding up or slowing down. Instead, the marble appears to speed up and then slow down and then speed up again. Hey, how flat is that table anyway? And how about the times? They weren't all the same, remember. If this was an 8, then that would be a 16, and the speed would be lower. And what about distance? It was 40 centimeters. But what if we were exaggerating a little bit by like half a centimeter? Then that would be 9.5, and the speed would be even lower. Of course, you are never allowed to monkey with the data once it's collected. All I'm saying is that this outlier is no reason to panic. Yet. It is enough, however, to make this average speed a bit too high. Hold on, though. That speed held for 30 centimeters, the others for only 10. Maybe a weighted average would be better. But let's find one line best fit to the data and its equation, because that slope will be a good velocity. This, however, is a problem. We expect our line to intersect the origin. Wait, maybe that could be our 6th point, and it would give us a new 6th speed. A millimeter isn't too much to worry about, but we could lock the line at the origin and get the type or the form of equation we want, speed number 7. But how convincing is this line? Answered with the R-squared test, which gives the percent of the variance explained by the equation. Predictions, it's not too bad. Predictions compared with measurements. Average those measurements, more differences. Sum up the numerator, same down there, 100% or darn close to it. The line explains all the changes in distance, but uncertainty is another question, and the root mean square error is part of the answer. More predicted values. Hey, this technique looks familiar. Summed up and divided. And this is about how far off our distance measurements were, apparently, which maybe reminds you of that half centimeter we looked at earlier. And it's the reason our computer preferred line number 5. Apparently, its predictions line up even better with our measurements, but we're sticking with number 6 and looking for speed uncertainty, which is essentially distance divided by time. Finding an average, and the details follow. Plugging in to find the standard error, and our value for speed number 8. But not all uncertainties are the same. This means there is a 68% chance that the true value for velocity is within this range. But extend that range to 2 standard errors, and you've got a 95% chance of it containing the true velocity, assuming it is a true velocity. Standard error is one thing. Standard deviation is maybe more familiar, so let's take a look at that. And to do so, we return to our 5 velocity values and take an average. You know the drill by now, our 10th speed. And this uncertainty is different. This time we expect 68% of all future measurements to fall within this range. It's a subtle difference, but it's a reminder that all this came from experimentation. And oh yeah, what about the rounding? What effect could that have had? In order to find out, we'll consider an extreme, drastic example. All values raised to the max. Only 10 chances in a million of something like this happening, and it would mean more time or a lower speed, but not that much lower. It still falls within our smallest uncertainty, so rounding, yeah, it's still necessary, but still dangerous. And that's not really even the question. The question was, how could this graph save your life? It's because life is a collection of choices. Keeping it simple, or maximizing some quantity or another, or keeping it in line with a prior commitment. It's about fitting data and theory, fitting expectations with reality, adapting each to the other because neither one is perfect or perfectly understood at least. And those experiences, hopefully they're going to keep coming, unexpected ones too. And we expect that more data means less uncertainty, but it's not ever really going to go away. It's just going to be better understood, better defined. Because we do not demand perfection in the world, only in the idea. Good choices and clear ideas go together, and we demand clarity in our concepts. So if your theory explains everything perfectly all the time, throw it out. Or better yet, analyze it to see what you might be missing.